Okay, so today, guys, we're going to be talking about electric field strength. Essentially, we're going to take what we were discussing yesterday and just put some numbers on it.
Alright. No, what?
Woo!
Yeah.
Numbers!
What now?
Find the net?
Huh?
Net.
Alright, so, guys, before we proceed to that, though, real quick, I want to kind of review what we went through yesterday. Got a few practice problems here. I want you to try these three. Okay?
Oh, I love it.
Okay, try these three.
Yeah.
Oh my God.
Yes.
That's three problems.
I didn't drink about this.
Yes, you're about to find out. Armand, Grace, you're pretty good at
Can
this.
you explain it to those of us who
No.
Yeah,
Yeah.
can you explain it to those of us who are slacking off and didn't watch the video?
Yeah, no, I can't.
The arrows go away from the positive, right?
Yep.
Okay, good.
Some people want to come volunteer and do these on the board for me?
Oh, I can't.
Someone just
Oh, Lord. Y'all can do whatever color pleases you.
because they were repelling.
Who needs a
negative.
who needs kind of a
Refresher
rundown?
course?
Everyone.
Actually, me, Tom, I think I got this just fine.
Oh, I don't. Is that what your team looks like? I don't know what it is. Because I just
Somebody get the third one for me. The third one's easy.
I'm still working on my number 2.
Good third one. Yeah. Come on, do the third one. It's like one of those things like you try to avoid making eye contact.
Yes.
Eye contact, you know, that you
Exactly.
That's all I did was avoid eye contact. No. She would ask you like questions, not ask
Does anybody know?
Yeah.
I hate that.
Because that's how it works.
You take a split second to look up just to see if they're looking at you, and then
I don't know if it happens if it's in direct.
that
How do you know? The more lines, the better. I think
This one,
mine's
this
looking
one.
pretty good, guys. I think I got it.
This will listen to you. With this one, would it just repel all the way like down there and then come back up? Or does it go?
Okay, because this positive is closer to this positive than the negative, it's never the lines from this one are never going to go back. No. Because that one is more this one. This one, the lines from this one are always going to go in this direction because this one forces it away. Because that negative is never going to win over that positive.
Yeah, it's really messy, but I couldn't figure out.
It is. It's going to go. This one's going to push away. Okay, this one's farther away, so this is never going to get.
I feel like if they were like around here, they would get attracted each way, maybe. I don't know. What happens if it's in the direct center? It would just be like
If it's in the direct center, then nothing would happen.
just staying.
There'd be a net force of 0 because it's
Sweet.
Easy.
No fun of that.
Wait, I forgot my question. Alright, let's start with the first one.
Kelsey's on it?
Oh, does the curve of the line matter? Like, is that curve okay?
It
Or
can.
is
Yes.
it like that?
You get on my nerves.
Like, does the curve of the line make that big of a deal?
Like which
Yes.
way's curvy?
Well,
Well, look, it needs to curve away from the two positives. And it can't curve towards the positive.
Yeah, dirt.
It's not going to go straight away. It's going to be kind of at an angle, so not so easy.
well, I think I got all right. So let's
Mr.
not
Lynn.
start the last one.
That was pretty easy. I have a question. All right. So like, say if there was one right here.
Good job. Not a linear line.
Horizontal.
You never draw lines between two light charges.
It's not my hand.
I want it to
If it has a hole in it.
from here.
I mean, I cut up my old clothes and used them
Come
as
in this direction.
Oh,
And going out.
same way.
So if it goes down in this direction, going out.
Every time you move, I just don't work on
And then right here.
Yeah, they say you ain't
Hey, I got that one right. Except for my card. Like the curvature of the line, the way the line is.
I'll throw away my shoe.
Okay, all these are correct, guys. Any questions on those? Yes.
Now, where do I begin?
What are what now?
Are those protons and electrons?
These are. This is a positive. It's not. It could be a proton, but we're just gonna say this is a positively charged object.
Design up there, you know?
So it always goes away from the positive and towards the negative.
Yes.
And why are some of them curved?
Okay. What these are showing is not the path. What these are showing is what direction the force. And this should have a straight in. This is showing the direction of force at any point. Okay, so at this point, we're saying at this point the direction of force would be in this direction. And at this point, the direction of force would be on a positively charged particle. Yes. So the direction of force of the electric field on a positively charged particle would be tangent to that line. Okay, so the lines are curving because the direction of force is changing. What now? All right, so let's move on, guys. So remember, guys, an electric field is really just kind of a representation of force. Okay, so kind of think of it. I think of it as like a set of vectors representing forces. This is old stuff. It's yesterday. Okay. So how then are we going to measure an electric field?
By the thickness of the vector.
By what?
The density.
Well,
of the vector.
how are we going to? Okay, but that is true. How close the vectors are together. But if I want to put a number on an electric field, if an electric field is a set of force vectors, then how do I put a number on an electric field?
The net force. The net
Count how much force there is on a charged particle, right? Okay, so the electric field will deal with how much force there is on a charged particle. Because it's an electric force field. Okay, so that's how it's to deal with how much force there is on a charged particle. Okay, so to measure an electric field, guys, what we do is we take a charge. It could be a positive charge, it could be a negative charge, doesn't matter. We call it a test charge.
Can a test charge be negative?
Test charge can be anything.
But I thought you said they were always positive yesterday.
Uh-oh.
To get a number on the okay. The force away on a negative is equal to the force toward on a positive. They're just opposite sides.
Oh, so we were just
Well, we're
setting
just getting a number. Okay.
Okay.
So, but all we're doing right now, we're trying to measure the strength of the electric field. So it doesn't matter if it's positive or negative. We're just trying to get a number.
You don't remember the yes and no?
All right. So the first thing we do, guys, we take a test charge, we stick it somewhere, and we ask the question: is there a force on it? How would you tell if there's a force on it? If it moves, if it changes speeds, right? Okay, if it changes directions, okay. So we take it, we look and see if there's a force on it. The greater the force is on it, the greater the electric field is. Bam. Okay, so if it's got a big old force on it, then it's got a big old electric field.
Big old.
Okay, so we're going to have an equation for electric field strength. And our equation for the electric field strength, there's a slight issue with doing the electric field strength, and we don't want just force, okay? Because if I let my electric field strength just be related to force, well then obviously there's a difference between the force for a big charge and a little charge, right? If I have a big charge, it's going to be a big force. A little charge is a little force. So the test charge would then be affecting the field. We don't want the test charge to affect the field. Okay, we want the field to be the same for any test charge. Everybody following me so far? I know this is kind of complicated. Okay, so the strength of the electric field, guys, is going to be equal to the force on a test charge divided by the value of the test charge. Okay, so if you double the value of the test charge, it would double the force, but that doesn't change the electric field because the top and bottom would be multiplied by 2. That's called prime. Anytime you see a prime, you know you're dealing with a test object. It's just it's an asterisk. No, not an asterisk, but a single quote. What's that called? Apostrophe.
What's it called?
Prime.
No, the
Electric field strength. So that makes sense, guys? I mean, if you double the charge, you're going to double the force. And so by dividing by the charge, we essentially negate the effects of having the force in there. So that kind of begs the question, well, how do we know what the force is on the charge? That's kind of frustrating. And so to solve that problem, we can resort back to an earlier equation. And what we found in that earlier equation, guys, is we have two equations now. We have the electric field is equal to the force on Q prime divided by Q prime.
Wait, so the
Nice
top
Q.
is the force of the charge and the bottom is the what of the charge?
What now?
Magnitude?
Yes, the magnitude of the charge. Okay? And we know the force on Q should be equal to K, Q prime, over Q. And I'm going to call this second Q QS. That'll be the Q of the source of the electric field. So Q prime is the Q of the test charge, how much charge is on the test charge, and QS will be how much charge is on the source. Okay, that's just I'm using that. Okay, over R squared. If I substitute that in, then we find that an electric field is equal to K, Q prime, QS over R squared divided by Q prime. Okay, I have a Q prime in the top and the bottom, so they cancel. Okay, so what we end up with, guys, is an electric field is also equal to that electric field constant times the amount of charge on the source divided by how far away you are from the source squared. Okay, so there's my equation for the strength of an electric field. Not involving, that does not go on the equation sheet. All you got to do is substitution. Just plug it in. Cancel. 2 steps. Y'all can do that. Right? That's not hard. Y'all got that.
That's to find the force.
This is to define the strength of an electric field by a charge. So QS for me is going to be the charge on the source of the electric field. Okay, so for example, if I'm talking about, let's talk about the Van de Graaff generator. Okay, on the Van de Graaff generator, I'm building up charge on the surface. Okay, that would be the source. Okay, if I wanted to talk about me holding a little sphere around there and some charges were getting transferred between those, but that would be like a test charge. Okay, measuring the strength as I moved around. Okay, so QS would be how much is on the Van de Graaff generator. Q prime would be how much is on the sphere. Okay. What am I done?
Wait, what is that like?
Huh?
The strength of the charge particle or the source?
Q prime.
No,
E. E is the electric field.
and is that electric field any different than the equation that you just gave?
This is just 2 different equations. This is the same electric field. I'm saying, but the problem with this is it's hard to measure the force on a charged particle. So what we can do, we can also just base it off of the charge on the sphere or on the source. Okay. What y'all should have seen from that last little bit, guys, the strength of an electric field is not going to be absolute. It's going to be varying on distance. Okay, and that's because what we got was E was equal to KQS over R squared. Okay, so as the distance is increasing, my electric field is going to be decreasing as well. And we can actually see that in our drawings. Okay, because as I'm getting away, typically, the space between our electric field lines is increasing. Okay, so as the radius is increasing, the electric field strength is decreasing. Okay, and we're going to measure electric field strength in newtons per coulomb. Newtons per coulomb. What do you think we measure a gravitational field strength in?
Newtons per meter.
Get the right idea.
Per atmosphere. Gravitational force.
This is going to be cool when we get there.
Newton meters.
Somebody's going to get there in a second.
We've been there, bro. Think about it. Newtons.
Okay, the reason we divide by coulombs is because I don't want the value of the test charge to affect the field. Okay, well in gravitational, I don't want the mass of the test mass to affect the field. So it'd be newtons per kilogram. What's a newton per kilogram? A meter per second squared, right? A newton per kilogram is a meter per second squared. So we measure a gravitational field in meters per second squared, or in other words, the gravitational field is the acceleration. Remember, we said the acceleration is the same at any point? I mean, it's the same for any object.
I was about to say.
Same way as the electric field.
What is K in that?
It's right here. It's in your, should be in your equation sheet already, number 39. That's K.
So that, I didn't know if that changed because we heard something.
Same K. Okay, guys, remember, the direction of an electric field is the direction of force on a positive test charge. Okay, so an electric field should always be pointing toward a negative and away from a positive. Okay, and as we've said, guys, the farther you move from the charge, the weaker the electric field is going to be. Okay, so the electric field is that's not a constant. But there is a case where it's a constant, but it's not going to be today. Okay. It will be on Thursday. No, tomorrow. Yeah.
So is that why like most of those elements like 104 to 114 like unstable because then they have like strong bonds between the electrons and the protons?
That's a really great question. I'm going to take a break from what we're talking about to discuss that because it's really cool.
What was the question?
I think, well, actually, he might have talked about that in the video, but we'll still talk about it. Huh?
The awesome.
The guy. Okay.
He can talk about those electrons, those elements. Talk about like basic.
All right. In any atom, we have the protons clumped together inside with the neutrons. I'm going to represent them by circles, whatever. All right, so naturally, those protons should want to separate, right? Okay, but I mean, it's not like there's glue holding them together. We didn't get some rubber cement and hold them together. So what is holding those protons together?
That force that he was talking about.
Nuclear force.
Okay, it's called the weak. The strong nuclear force, okay? The strong nuclear force, okay? And one thing that's different about the strong nuclear force and the electrical force is the electrical force, while it does fade with distance, okay, the strong nuclear force really fades with distance, okay? So, with the electrical force, we get out to here, we see a difference in the force. the strong nuclear force we get out to here, it might be almost gone. Okay, so as this nucleus is getting bigger and bigger and bigger, then I'm getting farther and farther from the center, and so my strong nuclear force is getting smaller. So that's what's holding that together. Well, so I mean, my electrical force is getting huge because I'm getting all these protons, and it's not that affected by distance. Okay, so the electrical force at that point is ginormous. The strong nuclear force not as big, and so at that point, that's why we see radioactive decay. What? Does it deal with half-life or? Okay. So let me let's work a few example problems. Yeah. To be honest, guys, I don't like that first problem. It's too easy and stupid. So we're gonna go to the second one. Okay. Well, I mean, it's just a waste of y'all's time. You could be getting to your homework earlier if I skip that one. All right, guys. Number 2. What is the strength of an electric field that's created by a sphere? Okay, so if it's being created by the sphere, are we talking about QS or Q prime? QS, and it's not just because it's sphere, it's because it's source. So that's going to be QS is equal to 9.1 times 10 to the negative third coulombs. Okay. Okay, the strength that is created by a sphere. Okay, so that's my source. I'm going to, but I wanted to get all these numbers written down first. And the distance is 0.3, so that's my radius. And so it's asking me, what is the strength of the electric field? What is E? Okay, we've essentially done this equation already, but well, I'll just go ahead and walk through it. No. Okay, so E, the strength of my electric field, is equal to F on Q prime divided by Q prime. The problem here, guys, I don't have a Q prime. I have a QS. Okay, so we can substitute in for here, and so I get that the strength of the electric field, we've already done this, is K Q prime over QS over R squared over Q prime. Okay, so I substituted this equation in for that one. Okay, so Q primes cancel. And what I get, guys, is the strength of the electric field is equal to K QS over R squared. Plug it in, plug it in. So the strength of that electric field is going to be equal to, this is 9 times 10 to the 9th newtons per meter squared over coulomb squared times QS. And so the strength of the electric field is 9.1 times 10 to the 8th.
Yeah.
The bottom of your question.
9.1 times 10 to the 8th coulombs. Okay, so what that tells me, guys, is at 0.3 meters, there would be 9.1 times 10 to the 8th newtons of force on every coulomb of charge. Okay, so if I had 2 coulombs of charge, it'd be twice as much force. 3 coulombs of charge, y'all get a tenth, would be a tenth as much force. Okay, so the strength of the electric field tells me kind of how much force are we talking about. Okay, let me do one more.
Why is it more than the K force?
Why is it more than the K?
Yeah.
Because I'm dividing by a fraction.
I know, but like, isn't K the strongest force that's keeping those two together? It's like that's keeping the protons in being in the nucleus or something like that. Don't worry about it.
No, K is just a constant. Essentially, the problem is the electric field is not equal to Q over R. It's equal to Q over R times something. So we just tested until we found K, and we said, okay, that's what K will be. Okay, last one, guys. In the previous problem, okay, have the same electric field. How much charge should be placed on a 2 kilogram weight? In other words, now I'm looking for Q prime. Okay, to suspend it in air if it's below the sphere. So I'm looking for Q prime. how much charge. Okay, the mass of that object that's going to be suspended is 2 kilograms. And it's going to be in this other electric field, okay, where we have a QS of 9.1 times 10 to the negative third coulombs. All right, so if it's going to be suspended, I know that the electrical force needs to equal the gravitational force. Right? Okay, so the gravitational force is done by F equals ma. So the gravitational force should be 2. We haven't used the number 9.8 in a while, huh? So that should be 19.6. Okay, so I know that my electrical force, which is equal to K Q prime over QS over R squared, times QS over R squared, this needs to equal that. I'm looking for Q prime. I can zoom out a little bit. Okay, so I know my force is going to be equal to that. I'm looking for Q prime. Q prime is going to be equal to, move all this junk around, FR squared over KQS. Y'all know how to do that algebra, right? Okay. Okay, so therefore, guys, Q prime, the amount of charge on the 2 kilogram weight to make it suspend is going to be equal to 19.6 newtons times 0.3 meters squared divided by K times QS. And so that amount of charge, somebody, could have my calculator in front of me.
2.15 times 10 to the negative 8.
Okay, so 2.2 times 10 to the negative 8 coulombs. Not much charge. Didn't take much. If these were metal objects, what do you think would probably happen?
Go up. It'll go down.
Zap. And then fall down to the ground. Most likely that much charge right between them, charge dissipate, the object would fall. I can't say that with absolute certainty, but we'll actually be able to calculate that. So remind me in a few days. We'll run those numbers and we'll figure out if it's enough charge to actually, would it zap or would it levitate? I'm gonna speculate that it would zap, but I did make something levitate the other day, didn't I? The pith ball.
Can you levitate? Can you levitate?
Oh, yeah, that's awesome.
Is that the secret behind David's blame?
I don't know.
Yeah, how do people levitate themselves?
All right, guys.
So David